And we begin our last series on our transformations with our one and only non-isometric transformer, the one that doesn't actually maintain shape and size, is the dilator. So again, we will be talking about Mr. Dilator. We have gotten through all of our isometric transformers. They all maintained shape and size even after their transformation. And so the definition, so this is the first part on your notes, the definition of a dilation, specifically, is a transformation in which one object is larger or smaller than the other by a constant multiplicative factor. Okay, that just means that if we had a triangle, that if one triangle was twice the size of the other, we mean that one side is twice the side of its preimage. The second size is twice the size of its preimage, and the third side is twice the size of its preimage. So it's not that one side can be twice the size, one side can be 3 times the size. It's by the same, that's what I mean by constant multiplicative factor. Now here is dilator. And you might be thinking, well, dilator looks pretty lame, and hey, look, someone's actually holding the gun this time. So dilator's special ability is to change size. You can get bigger or smaller. So when confronted with a French fry looking shape here, with an old 17th century style handgun here, Dilator comes along and goes, "Oh, you're going to shoot me? I don't think so. I'm going to eat you. Yum, yum, yum." And then the guy's like, gloop. He goes down in his tummy and he's like, "Oh, that was a delicious French fry, man." And that's Dilator for you. He's pretty BA. Now, every dilation has a center, and the center is, you can kind of think of the root from where it will grow or shrink from. And it has a scale factor, which is that constant multiplicative factor I referred to earlier, that indicates how many times bigger or technically smaller our shape will become. A dilation is considered an enlargement if the scale factor is greater than 1. So if you multiply something by 1, it stays the same. But if you multiply a number by something larger than 1, then it gets larger. And there's our enlargement. So we have little mini Mario, regular Mario maybe, big Mario, jumbo Mario, I think it's how it goes maybe. I don't know, I stopped with the Super Nintendo, so I have no, I had it in 64, never mind. But after that, I'm kind of lost. I never had a Wii or Wii U or GameCube. A dilation is called a reduction if the scale factor is between 0 and 1. So this is where we start getting into our fractionals, like 1/2 or 2/3 or 3/4 or 1/4. It can't be 1 because then it would be the same exact size, and it can't be 0, otherwise it'll disappear. It essentially turns into a point instead of an actual object. So any fraction between 0 and 1 will be considered a reduction. Now, does that mean all fractions are a reduction? No, because what if I talked about a scale factor of 7/2? Well, that's really 3.5, so the shape would be growing 3.5 times larger than it would be. So a fraction doesn't guarantee a reduction. Now, dilations have rules just like translations, reflections, and rotations did. Now, the dilation rule is going to be kind of like a translation rule, except a translation rule, let me just write it down real quick again, was where we had x comma y, and x could change some factor a, and y could change some other factor b. A and b could have been the same, but it didn't have to be the same. So that was for a translation. Now, translations had an additive property to it, where we added or subtracted a certain amount from x, and we added or subtracted a certain amount from y. But with a dilation, the scale factor, there's only one specific number here. And that specific number is going to affect both x and y. And I mentioned earlier, it is a multiplicative factor, so it's going to be multiplying with x and y. So the rule just looks like this. It's a times x, and it's also a times y, where a is our scale factor. And again, this rule only works when the center of the dilation is at the origin, at 0, 0. If the center is not at 0, 0, then simply multiplying by a and getting new image coordinates will not work the same way. But we'll do an example where the center is not at 0, 0, so you'll know what to do. So the first example we'll look at says determine the coordinates of -5, 18 after a dilation with scale factor of 1.42 and a center at 0, 0. Okay, so we're going to need our calculator here. So our x comma y, let's get our rule up here. So again, our rule was x comma y, and then ax, ay. Well, a is our 1.42. So that's going to go there and there. And then our x, well, negative 5 was our x, and 18 was our y. So that's all we're really going to do. We're going to take our old x and our old y, negative 5 and 18, and multiply them both by the same amount, 1.42. Okay, so we didn't really give that point a name, did we? So we'll just write it here. We'll say image. Image equals. So if we take negative 5, so my calculator, negative 5 times 1.42, I get negative 7.1. And if I take 18 times 1.42, I get 25.56. And those are the exact decimals. I didn't round those at all. Those are it. If you only have 2 to 3 decimals in an answer, I would just keep them all personally. I wouldn't round it and just chop off 1 decimal. Just leave them all, okay? Only if your calculator, has 9 or 10 digits, then you probably want to round it to, say, 2 decimal places, maybe even just 1. So that's how we're going to work our dilations. There's our image. There's the new spot. All right, so let's try a little bit different one here. It says, given triangle ABC with A at 4, M, B at negative 10, 4, and C at negative H, P, determine the coordinates of a dilation with scale factor 7/2. Now, I don't have it on here, but I'm pretty sure I have it in your notes where the center's at 0, 0. Okay, so our rules will apply. Now, one thing you probably notice is we can't really graph 4, M. We can't really graph negative H, P. We don't know what those values are. True, but it doesn't matter. So A prime is just going to be, get a little thinner here. So we're going to take our scale factor, 7/2, and we're going to multiply it by 4. And we're going to take our same scale factor, 7/2, and multiply it by m. Now, let's simplify this. 7/2 times 4, well, the 2 can cancel the 4 and leave the 2 left over, and so 7 times 2 is 14. Now, I can't really do anything with 7/2 times m. It just stays that way. So you can either write it like this, 7/2 m, or what you could do is put the m up with the 7 and just make that one singular fraction of 7m all over 2. Either way's fine. I would probably personally write it as, the fraction as the numerical part, and then just m kind of off to the side being multiplied with the 7/2. So there's A prime. B prime. Again, we're still multiplying with 7/2, but we're going to multiply with negative 10 for our x, and we're going to multiply with 4 for the y. Well, we can go ahead and knock out this part over here because it's the same thing we did as the x coordinate for A prime. 2 knocks the 4 out, leaves a 2 factor left over, so we know we're going to get 14 for our y coordinate. Then over here, 2 cancels out with the 10 and leaves a factor of 5 left over, so it's 7 times negative 5, so it ends up at negative 35, 14. And last but not least, C prime. So we're going to take our 7/2 and we're going to multiply it by negative h, and we're going to take our 7/2 and multiply it by p. So you're going to quickly see here, if your scale factor is being multiplied by variables, it actually ends up being an easier problem because there's no simplifying really to be done for the most part. So 7/2 times negative h, well, we're going to write the negative part first, and then it's just 7/2 h. We can't really do anything with that. And the same thing with 7/2 times p. It's just 7/2 p, and we're done. And so there's A prime, B prime, C prime. Number 3, if m has coordinates of 5, negative 10, and m prime, the image, has coordinates of 17.5, negative 35, determine the scale factor when the center is at 0, 0. So since our scale factor is at our typical 0, 0, our rules will apply, but this is kind of like a We know the beginning part, we know the ending part, we just need to know what happens in the middle. So if you think about it, here's the situation we got going on. We have m, which is 5, negative 10, and we're multiplying it by something, aka our scale factor, and the answer, m prime, needs to be 17.5 comma negative 35. So we aren't doing the multiplication, it's already been done for us. So if we want to go backwards, what's the opposite of multiplication? We need to divide, okay? So we're going to take our image, say 17.5, and we're going to divide its pre-image coordinate, which was 5. So if I throw that in my calculator real quick, 17.5 divided by 5, I get 3.5. Now, just to double check here, I should get the same result if I took my y image coordinate and divided it by my y pre-image coordinate. So negative 35 divided by negative 10, negatives cancel. Dividing by 10 just moves the decimal point 1 over to the left, and I do get 3.5 again. So my scale factor is the 3.5. And we're done. Now let's look at some stuff with graphs, okay? So we just did all the point stuff. Now we're going to work on a couple graph examples. So it says, given triangle ABC, draw the dilation with a scale factor of 1/2 and a center at 0, 0. So technically our rules apply here. So if you really wanted to, you could write down the coordinates for A, B, and C, and then cut everything in half and then graph those points. You could certainly do that. So for example, A here is at 1, 2, 3, 4. It's at negative 4, comma 4. And so if we applied our scale factor of 1/2, then A prime would just be at negative 2, comma 2. So negative 2, 2, there's A prime. Okay? You can do it this way. Okay, this is an option. I want to show you, maybe without using the rule as much, how you could still do this. Okay? Now, the one thing I note is that yes, you kind of think of slope here. To get from the center, which was at 0, 0, to point A, I'd have to rise 4 and run 4. Now, my slope, I'm going to write it this way, is rise over run. My rise was a plus 4, and I'm always starting at my center here. So I rose 4, and then I ran to the left 4, which is a negative direction. Okay? Now, what I can do is take my rise and my run, apply the scale factor of 1/2, and so my new rise would be plus 2, and my new run, if I cut it in half, would be negative 2. So now go back to the center, back here at 0, 0, and now apply this new slope. So go up to plus 2, and then run negative 2 would be to the left. And I still end up at negative 2, comma 2. So there's where my A prime is. So there's a second way that you could do this. So let's look at B. Okay. Now again, I'm going to look at slope, rise over run. And from the center, I'd have to rise 1, run 2. So that was a plus 1 direction and a plus 2 direction. Now I want to apply my scale factor, multiplying by 1/2. And so my new rise would be, well, 1 times 1/2 is 1/2. And sometimes this is going to happen where you're going to get a fractional rise or run number, and that's fine. So 2 was my run. If I multiply that by 1/2, I get plus 1. So now I'm going to apply this slope starting from my center again. So I'm going to rise 1/2 a unit, which puts me right around in here, and then I'm going to run over 1, which puts me right there. Okay, and from the center to B, if we were to look at this distance, does it look like this point is halfway between? Yeah, I think it looks pretty good. So there's B prime. Let me erase some space here. We'll get rid of that, get rid of that, that and that. We'll just reuse it for C. So C, if I look at my rise and run, I would rise technically down 3 and run nothing. So my slope would be negative 3 over 0. Okay, so now multiply it by 1/2. 1/2 of negative 3 would be negative 3/2, or negative 1.5, negative 1.5 I could say. And 1/2 of 0 is, well, still 0. So if I rise negative 1.5, that means I'm going down 1.5 and then I run nothing. So I'm right here. So this is the point that's halfway between the center and C. And so there's C prime. Now we just need to connect our dots. So A prime, B prime, B prime, C prime back to A prime. And you can see that our A prime, B prime, C prime, our image triangle, is kind of shrinking towards the center at 0, 0. Okay, and it's pretty much halfway, if you notice. This distance between A and A prime should be the same distance between A prime and the center. There's our half factor. Again, just like we showed earlier, from B to B prime and B prime to the center is the same distance, so it's halfway. And likewise with C to C prime and C prime to 0, 0, it's the same distance. So there's our half factor once again at play. So you've got two options if the center's at 0, 0 and you're doing it graphically. I like using this slope method if you wanted to figure out the coordinates for your points and then multiply everything by half and regraph those new image coordinates. You certainly could. You'll get the same exact answer. All right, the last example. Again, I promise you we're going to look at a dilation where the center is not at 0, 0. So let's take a look at this one. This time the center is at 5, 8. So let's find out where that is. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. So there's my center. There's where things will be growing or shrinking from. So we're still going to use the same idea that we did in the last example, or the way I used to do it anyway, with slope. Okay, since our center's at 5, 8, our rule no longer applies. Okay, you can't just look at the coordinates for A, B, and C, multiply the x and y by 3 halves, and regraph those points and you're done. It's not going to work this time. That's why I like to prefer this slope method. Okay, so this is what's going to be somewhat maybe a little trickier here. Let's start with B. B's closest to the center, so let's knock it out first. So the slope is we go down 1, 2, 3, and to the left 2. Now, we can look at this one of two ways. Going down 3 is negative and left 2 is negative, so really I have positive slope. Okay? So when we're talking about B, the rise and the run, we rose -3 and we ran over -2. Okay? Now, we still want to use this scale factor of 3 halves. So this is where we're going to take these and multiply them by 3 halves. So our new rise, so 3 halves times -3 is -9 halves, which is -4.5. And our new run would be negative, or 3 halves times -2. So if you were to look at that, the 2's would just kind of knock each other out, because this is really the numerator, that and the denominator. The negative stays, and we'd get -3 as our new run. Okay? So now what we do is we go back to the center, and we're going to rise -4.5. So we're really going to go down 1, 2, 3, 4, and then half. So we're right here technically. That's not my point though, but that's where I'm at, right there. And then I'm going to run over to the left 3. 1, 2, 3. And notice I keep staying on those halfway marks. So right here, there's B prime. And notice this distance, not really distance, but this direction, I should say, between the center, B, and where B prime is. They all line up. Okay? B prime is 1.5 times longer, the 3 halves, it's 1.5 times longer than B is to the center. So you can consider this like a ×1 scale factor, and B prime is times 1.5, which is the 3 halves. Okay? So if I were to take the halfway mark between the center and B, there's a half, and that's how much I just added on beyond B. So let's get rid of all this now. All right, now let's try it with, let's say A. Okay, so let's erase all this extra stuff here. Let's get a new rise, let's get a new run. I'm going to keep the 3 halves there, but I'm going to get new image slope numbers to work with here. Okay, so now for A. So again, start at the center where everything grows and shrinks from, and let's figure out what the slope is to A. So again, rise over run. So I go down 1, 2, 3, 4, 5, and then over 1, 2, 3, 4, 5, 6, 7. So I rose -5 because I went down, and then I went to the left 7, which is also negative. So it is a positive slope, but we need to keep them as the negatives, okay? Because we need to keep going in that same direction, that it's really a negative direction. So now we multiply both of these by 3 halves again, okay? So -5 times 3 halves, -5 times 3 halves is going to give me, what, -15 halves? AKA -7.5. Okay, and if you just want to type this in your calculator, that's absolutely fine. Go ahead and do that. Then -7 times 3 halves would be -21 halves, which is another way of saying -10.5. So here's our new slope we want to use back at from the center at 5, 8. So we want to rise -7.5. So 1, 2, 3, 4, 5, 6, 7.5. So again, I'm right here between the x-axis and coordinate C there. But now I need to go over to the left, since it's -10.5. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here's right here 10, and now I need to move over half a space. So technically, I'm right in the middle of that square right there. All right, so that is where A prime should be located. Now, again, if I line up, my A prime A and the center should all line up perfectly straight. Let's double check. Hey, check. That's all lining up, so I know A is growing in the same direction, or A prime is growing in the same direction as A is from the center. So that checks out. And again, this distance right here, that's kind of like our times 1 factor. And so how much is this extra? That's a half factor. If you were to look at this distance, it would be this half distance between A back to the center. So let's try one more. Let's go with C. Let's figure out where C prime is. So let's erase this. We're going to get a new rise, a new run, new rise, new run. And again, sometimes you guys are just going to get decimals and you're just going to have to work with it. You're just going to have to estimate on your graph where approximately that's at. So let's see, slope for C. We're going down 1, 2, 3, 4, 5, 6, 7, and we're running nothing. So rise is -7, run is 0. Okay, so now let's multiply our rise and run by our 3 half scale factor. So -7 times 3 halves, that's -21 halves, aka -10.5. Our run of 0 times 3 halves is still 0. So we're still not going to move anything left or right. So now again, go back to the center, and we're going to apply our new slope. So -10.5. Well, here was 7 down to C, so I'm just going to count from here. So here's 7, 8, 9, 10, and then I need to go half. So right there, there's 10.5 below, 10.5 negative from our center, and now I need to move over nothing. So really it's that spot. And there's C prime. So now, since we've done all of our points, we just need to connect now. A prime to B prime, B prime to C prime, C prime over to A prime. And you can see that A prime, B prime, C prime is larger than triangle ABC. How much larger is it? Well, each side grew by 50%, okay? Because again, think of 3 halves as 1.5, split up the 1 from the 0.5. The 1 represents the original 100% that triangle ABC is, and the 0.5 really represents an extra 50% of growth, okay? So A prime B prime is 50% larger than AB. B prime C prime is 50% larger than BC. And A prime C prime is 50% larger than AC. Okay, so again, I like to use this slope method, and hopefully you like it too. And what's kind of cool is you can kind of get like this telescoping effect, I guess we could call it. that if we started doing other scale factors on this same graph, it starts to look kind of cool. Let's use green here. So if I were to connect together my A and A prime, B and B prime, you start to kind of see like this 3D looking effect. Okay, maybe you guys can see it here, hopefully. Let me use a different color here. Let's use A. Let's say I had this point as A double prime, and I'd want a parallel line to these other two lines here. So I think it would probably end up maybe right there. Notice how this line I just drew in looks like it's parallel to A prime, B prime, and it looks like it's parallel to A and B. And then from here, I want a parallel line that's going to connect to this. That looks pretty good, I think. So this looks like it's parallel to B prime, C prime, and parallel to BC. And then lastly, this should look pretty parallel too. I think it's going to end up about right there. This looks like it's pretty parallel to A prime, C prime, and to AC. And so there's another triangle. I don't know how much larger this is because I was just kind of making it up on the spot. But you can kind of see how these triangles look like they're coming out at you and they're getting larger and larger. That's the idea behind a dilation. Okay, so these three triangles, they're all technically similar to each other. They're not congruent to each other. They're not the same size, but they're all similar, which is a chapter that we'll get into later next semester. So anyway, I'll stop bugging you guys with that. I just kind of want to show you that's kind of a cool extra thing there. And so the next video, the last video of the chapter, we'll discuss doing dilations like this without the graph. So we're going to need compass and protractor again. So that is all for this video. We'll see you on the next one.